Welcome, welcome, Ishik Boys high school students. And a very special shout out, to Mr. Jeeger's physics class. You're diving deep with us today here on For the Love of Physics. So today, we're not just, flipping through pages, we're really launching into fluids in motion. Now, what does that actually mean? Well, for me, it's all about figuring out how liquids and gases, how they act when they're moving.
Right, stuff that flows.
Exactly.
Right.
Think about a river rushing past or the air moving over an airplane wing, even like how blood flows through your veins.
It's everywhere.
It really is. It's all fluids in motion all around us. So our mission today for this deep dive, it's to unpack some of these key ideas about fluid flow.
Yeah, the fundamentals.
Connect them to things you see every day and hopefully make your physics textbook kind of come alive right here.
Sounds good.
Okay, let's kick things off with something like super relatable. Imagine you're out canoeing or maybe even whitewater rafting.
Oh yeah, I can picture that.
You know those times? Sometimes you're just gliding along, smooth sailing, right? Calm stretch of river. The water just flows around the boat almost like glass.
Very peaceful.
But then, bam, you hit a section with rocks, maybe a sharp bend, and suddenly it's all foamy, swirling, crazy whitewater rapids.
Totally different feeling. Much more intense.
Completely. And that river picture, it's actually a really good way to start thinking about the two main ways fluids can flow. We call them laminar and turbulent.
That river analogy is perfect, actually. Those smooth, calm parts you mentioned, that's exactly what we call laminar flow.
Laminar, okay.
And in laminar flow, every little bit of fluid, every particle, follows the same smooth path as the one that came before it. We call these paths streamlines.
Streamlines, like lanes on a highway.
Sort of, yeah.
Yeah.
And the really key thing is these streamlines, they don't cross each other. It's all very orderly, very predictable, like that smooth river section.
So when you say streamlines, are we talking about like the actual tiny water molecules, or is it more the overall pattern?
That's a great question. It's more about the overall pattern. Think of streamlines as showing the average path a little parcel of fluid takes. They give you a visual for the direction and smoothness of the flow.
Got it. Smooth and predictable.
Exactly. But then you have those foamy whitewater rapids, right?
Yeah, the chaos.
That's turbulent flow. It's completely irregular, chaotic motion. Instead of neat streamlines, you get these wild swirling things called eddy currents.
Eddies. Like little whirlpools?
Kind of, yeah. Little swirls on unpredictable movements. You see turbulent flow behind a big ship cutting through the water, or, the air currents in a big thunderstorm.
Definitely not predictable.
Not at all. It's chaotic.
Wow. Our source material had this picture, water flowing around a cylinder. You could literally see the smooth lines.
Wonderful, yeah.
And then behind it, just this mess of swirls. The turbulent part, the difference is just huge.
It really is. Laminar is organized. Turbulent is, chaos.
So predicting turbulent flow must be incredibly hard then, if it's so chaotic.
Oh, absolutely. It's one of the biggest challenges in physics and engineering. Those eddy currents mix everything up in ways that are mathematically incredibly complex to describe perfectly.
And that causes problems in the real world?
Huge problems. Turbulence increases drag on cars and planes, wastes fuel. It wears out pipes faster, makes weather forecasting harder.
Wow.
Yeah, figuring out how to manage turbulence is a massive deal. It affects efficiency, safety, lots of things.
Okay, that puts it in perspective. It's not just a textbook term.
Definitely not.
All right, let's unpack this next big idea then. Sometimes in physics, right, to understand really complicated stuff.
We simplify.
Exactly, we make simplified models. Like an architect's drawing isn't the real building, but it helps you get the idea.
Good analogy, yeah.
So for fluids, we often use this concept called an ideal fluid. Now, gotta remember, no real fluid is perfectly ideal.
Right, it's an idealization, a tool.
But it's super useful for getting a handle on the basics.
Precisely. This ideal fluid model helps us build our understanding. And it has 4 key characteristics we assume it has.
Okay, 4 things. What's number 1?
First, it's incompressible. That just means its density always stays the same. Constant density.
Like water. You can't really squash water much.
Exactly. Most liquids are pretty close to incompressible, so you don't have to worry about density changing as it flows, which simplifies things.
Okay, incompressible.
Got it. What's next?
Second, an ideal fluid is non-viscous. Viscosity. That's basically the fluid's internal friction, like how thick or sticky it is.
Like honey versus water, or different motor oils.
Perfect examples. Motor oil viscosity is key, right? Thick oil for hot weather, thin for cold. Real fluids lose energy to this friction, turning it into heat.
Right.
But an ideal fluid, zero viscosity, no internal friction at all, no energy lost that way.
Because an ideal honey would pour like water.
Yeah, pretty much. It wouldn't resist flowing at all, which is, not how real honey works.
Definitely not. Okay, so incompressible, non-viscous.
Yeah.
What else? Third is steady flow. This means if you pick any point in the fluid, the velocity, density, and pressure at that specific point always stay the same over time.
So it's not changing moment to moment at one spot.
Correct. Constant conditions at any given location. And finally, number 4, it's non-turbulent.
Linking back, so no eddy currents.
Exactly. The flow is always smooth, always laminar for an ideal fluid.
Okay, so those 4 things. Incompressible, non-viscous, steady flow, and non-turbulent. It's like the physics equivalent of assuming a frictionless surface, right?
That's a great way to think about it, yeah. It strips away some real-world complexities so we can see the underlying principles more clearly.
It helps build that foundation. Even though it's not perfectly real, it gets us started.
That's the idea.
Okay, now here's where it gets, I think, really interesting. Connecting this to something you probably do all the time. How does the speed of a fluid change when it moves through, like, different sized pipes or openings? Think about a garden hose.
Okay.
You put your thumb over the end, right, to make the water spray further.
Yeah, everyone does that.
Why does the water suddenly shoot out so much faster? It's not like you turned up the tap.
No, it's not. It's physics. It comes down to a core principle. Conservation of mass.
Conservation of mass.
Okay,
Yeah.
for an ideal fluid, remember, it's incompressible, the amount of mass flowing into a section of the hose in, say, 1 second.
Has to be the same amount flowing out in that second.
Exactly. You can't magically create or destroy water inside the hose. Mass is conserved.
Right.
And this leads us straight to something called the continuity equation. It looks simple. A1V1 equals A2V2.
A1V1 equals A2V2. Okay, break that down. A is
the cross-sectional area, so like how wide the opening is.
the size of the pipe.
Yeah, and V is the fluid speed. So A1V1 is the area times the speed at one point.
And A2V2 is the area times the speed at another point.
Correct. And that product, A times V, we call the flow rate. The continuity equation tells us this flow rate, AV, has to stay constant all along the pipe.
Okay, constant flow rate. So back to the hose.
Yep. When you put your thumb over the end, you make the area A2 much smaller, right?
Yeah, definitely smaller.
So if A goes down, but the product AV has to stay the same.
Then V, the speed has to go up.
Precisely. The water has to speed up to get the same amount through the smaller opening in the same amount of time.
That makes so much sense. And it explains why rivers flow faster in narrow bits too.
Absolutely. Where the river channel narrows or gets shallow, the area A decreases, so the water speed E increases. Same principle.
Wow. So just by looking at the size of the space, you can predict how the speed changes. That's actually really cool.
It is. And engineers use it constantly, designing plumbing, nozzles, even understanding blood flow in arteries.
Right, narrower arteries would mean faster blood flow there.
Potentially, yes, though blood is more complex than an ideal fluid. But the basic principle applies. It's fundamental.
Okay, so speed changes with area, but what about pressure? How does pressure fit into all this?
Good question. They're connected too.
Our source had this example. A leaf floating in a drainage pipe. When the pipe got narrower, the leaf sped up.
Continuity equation, yeah.
Right, but why did it speed up? What pushed it faster into the narrow bit?
That brings us to another huge idea in fluid dynamics. Bernoulli's principle.
Bernoulli.
Yep. And Bernoulli's principle states it really clearly. The pressure in a fluid decreases as the fluid's velocity increases.
Wait, so faster flow means lower pressure. That seems counterintuitive.
It can feel that way at first, but think about that leaf. To accelerate, to speed up, Newton's second law says there must be an unbalanced force pushing it forward, right?
Right, EVMA. Need a net force.
So where does that force come from? It comes from a pressure difference. The water pressure behind the leaf must be higher than the water pressure in front of the leaf, where it's entering the faster, narrower section.
So the higher pressure behind pushes it into the lower pressure, faster moving area.
Exactly. That pressure difference provides the push. Higher speed corresponds to lower pressure along the streamline.
Wow. Okay. And this explains airplane wings. How does that work?
It's the key. Airplane wings, or airfoils, are shaped specifically, usually more curved on top, flatter on the bottom.
Yeah, you see that shape.
That shape makes the air going over the curved top travel a bit further and therefore faster than the air going underneath.
Okay, faster air over the top.
So Bernoulli's principle tells us faster air means
Lower pressure.
lower pressure above the wing.
Yeah.
The pressure below the wing where the air is moving slower, is higher.
And that difference pushes the wing up.
That pressure difference creates the upward force we call lift. That's what gets the plane off the ground. It's brilliant engineering using physics.
That is brilliant. Okay, and there's this paper trick you mentioned.
Oh yeah, try this. Seriously, grab a sheet of paper, hold the short edge just under your lower lip so it hangs down.
Okay, like this?
Yep. Now blow hard over the top surface of the paper.
Sound of blowing. Whoa, it lifts up,
See? You made the air move faster over the top.
lowering the pressure there.
And the normal, higher atmospheric pressure underneath pushed it up. Simple demonstration of Bernoulli right there.
That's fantastic. Easy to try.
It really brings it home. Now, this Bernoulli's principle, the pressure-speed link, it's actually part of a bigger picture, a more general equation called Bernoulli's equation.
Okay, more math.
A little, but it's about energy conservation. The equation looks like P plus 12 V2 plus RUC equals constant.
Whoa, okay. P is pressure.
Right. That 12 V2 part, that's related to the kinetic energy of the fluid, the energy it has, because it's moving. ROC is density, V is speed.
Kinetic energy per volume. Okay. And the last bit, RUC.
That's the potential energy part, related to gravity. Rho is gravity's acceleration, H is the height, so it accounts for the fluid's elevation.
Okay.
The whole equation basically says, along a streamline in an ideal fluid, the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume stays constant. Energy is conserved.
So if one part changes, like the speed of use goes up?
Then something else has to adjust to keep the total constant. If the height H stays the same, like in a horizontal pipe,
And the what part doesn't change.
right, so if I goes up, P pressure must go down. That's how the equation simplifies back to Bernoulli's principle for constant height.
Ah, so the principle is a special case of the bigger energy equation.
Exactly. The full equation lets you handle situations where height changes too, like water flowing out of a tank.
Right, like figuring out how fast water shoots out of a tap at the bottom of a tall tank.
Precisely. You can use Bernoulli's equation, knowing the pressure at the top surface and the height difference, to calculate the exit speed. It's very powerful.
It really ties everything together. Pressure, speed, height, energy.
It's a cornerstone of fluid mechanics.
Okay, wow. We've covered a lot of ground in this deep dive into fluids in motion.
We have indeed.
We started with the difference between that smooth, predictable laminar flow
Like a calm river.
and the chaotic, swirling, turbulent flow with its eddy currents like rapids. Then we looked at the ideal fluid model, that useful simplification assuming it's incompressible, non-viscous, steady, and non-turbulent.
A necessary starting point.
Then we hit the big principles. First, the continuity equation, A1V1 equals A2V2.
Showing how speed changes with area. The garden hose effect.
Exactly. And finally, Bernoulli's principle, faster flow, lower pressure, and the bigger picture with Bernoulli's equation, connecting pressure, speed, and height through energy conservation.
Vital for understanding lift and so much more.
So here's a thought for you all listening. Next time you're, watering the garden or just watching a river, maybe even seeing leaves blow down the street, think about these physics principles. Can you spot laminar flow or see where things get turbulent? Or maybe think about a fast car zooming past you, what's happening with the air pressure around it.
Yeah, how does Bernoulli apply there?
It really makes you see the world a bit differently, doesn't it? How much of this is happening all the time, unseen, but following these rules?
Physics is everywhere.
It truly is. Okay, that wraps up our deep dive for today. Stay in contact with your physics teacher, stay creative,